focus on program equivalence checking and software verification. He's a PhD student at Rutgers.
Okay, thank you. I hope everyone can hear me. Like, can everyone hear me in the back, or is this? No? Good? Okay, great. So today I'll be presenting our work exploring locally bounded translation validation. So to start off some motivation, imagine you were checking some code where you were asking an LLM to optimize the code for you. So let's say you have the C program, source.c, and you ask the LLM, optimize this program for me, and it outputs target.c. So how do you know target.c is actually correct? Meaning the optimizations the LLM performed were, they preserve the semantics of the source program. Essentially what this means is for all inputs to both of these programs are the outputs equivalents. So that is our notion of equivalence. It could be, by output, I could mean the return value as well as maybe the state of the heap after the function executes. So these can be like, imagine they're functions. I wrote their programs here, but imagine they're functions. So how do we check equivalence of these programs? Well, one way to do this is with a translation validator. So translation validators were originally used in the context of checking compiler correctness optimizations. So the idea was your compiler does some optimizations, multiple passes on a program, and a translation validator it's not aware of which optimizations were exactly performed always. It will just take in these two programs and it will check that they are equivalents, or in lighter terms, maybe one refines the other. So in the general case, when you have programs or functions where you have unbounded numbers of loops, this is an undecidable problem, checking the equivalence. So what we do in practice is we use bounded translation validation. And essentially what bounded TVs do is they under-approximate program behaviors by unrolling loops up to a user-supplied bound. So for example, let's say you have this unbounded while loop here, and the user would provide an unroll bound. Let's say they provide 2. And then the bounded TV would unroll these loops by that user-supplied bound. So here we've unrolled the loop twice. And essentially what this does is it simulates the behavior of the loop up to 2 iterations. And this is inherently an under-approximation. So if your bounded TV finds a bug in this bounded program on the right side, that bug exists in the original program. If the bounded TV does not find a bug, that does not necessarily mean there's no bug in your original program, right? So if there's a bug and you don't find it, you may have to increase your unroll bound. And sometimes you may not be able to even increase it far enough, right? So that's why it's an under-approximation. So let's do a concrete example of bounded translation validation. So let's say we have P and P prime. These are 2 programs. And to check equivalence, given all sets of the same inputs, we want to check whether the outputs match. And in this case, the outputs are going to be these arrays I fed in. So we want to check the heap states after you execute this matches. So these programs are actually not equivalent because in P prime, we have this guard stated, this if statements before the main computation. So when j is equal to 1, the behavior of these 2 programs diverges and they're not equivalent. So let's try to use a bounded TV to find the bug here. So let's take that buggy function I had and let's unroll the loops. So what we would do is, let's say we give a global unroll bound. So traditionally, you give one unroll bound, and it applies it to all loops. So let's say we unroll everything once. That's our global unroll bound. We'd first unroll this inner loop. So we unroll the inner loop by 1 iteration. So we simulate 1 iteration. And then we unroll the outer loop, which is the yellow there. And after we've done that, we see the bug is not observable here because the if statement here is triggered when j is equal to 1. So here, that is not the case. So to find this bug, we need to actually increase our unroll bound. So let's do that again by increasing the global unroll bound. So let's try it again. This time, we unroll the inner loop twice. So now that inner bug will be triggered. And since we're doing global unrollings, we also have to unroll the outer loop. But now we get this code blow up. And the bug actually can be triggered in 2 ways. There's 2 program paths now that will trigger that bug. And this sometimes can be inefficient. It could lead to timeouts. So really what we want is maybe some way to do a local unrolling. Maybe we can unroll the inner loop just once, and then unroll the inner loop twice, and then the outer loop once instead, so we don't lead to this code blow up. So this is where we introduce a very simple idea that's been around in bounded model checkers, but presently not for bounded TVs like Alive 2. So we present local unroll bounds. So basically, you just apply single unroll factors to loops, and you can they're user supplied the same way global unroll bounds are, and you can do fine-grained verification. And in the next couple slides, I'll show you how this can be useful for actually exploring unroll bounds. So we implemented. So actually, let's go over what this global unroll bound scenario looks like with Alive 2, which is a state-of-the-art translation validator for LLVM IR. So it's used in the LLVM developer pipelines, found like hundreds of bugs. So right now it just supports global unroll bounds. So what usually happens is, let's say you have some program, there's a bug in it. You provide these global unroll bounds of 1. LVM says, Alive2 says, everything looks correct. So then let's say you know there's a bug. You're like, OK, so maybe I need to increase my unroll bound. You increase it to 2. It still says everything looks correct. So you try to increase it again. Now, and then you wait and wait and wait and wait. And then there's a timeout, possibly because there was some sort of code blow up if you had multiple loops, right? So with local unroll bounds, you can just provide these comma-separated lists of unroll bounds, 1 per loop. And Alive2 may actually give you a concrete counterexample, and it'll say it found the bug because it's not restricted by that code blow-up problem we had with global unroll bounds. So now that I've introduced local unroll bounds, let's go over some properties of unroll bounds. So for global unroll bounds, there's this nice property where if you do verification with a global unroll bound of I+1, and your program is verified to be correct, that implies a verification using global unroll bounds of I. And the proof idea for this is that just the program paths in your bounded program. So on this left-hand side, let's say I have a unroll bound of 1, and on the right-hand side I have 2. The program paths on the left-hand side program are all contained within the program paths on the right-hand side program. So the right-hand side program is correct. That would imply the verification of your left-hand side program. And the right-hand side program has many more paths that are not captured here. But this global unroll bound property, when you take this monotonicity property, that's what I'll call it, when you bring it to the local unroll bound world, you have this different property where, in this case, we have this total order, meaning for all pairs of elements where I verify I+1, everything under I+1, any unroll bound less than I+1, is verified by verifying this larger thing. So with local unroll bounds, this property actually does not hold. So these unroll bounds introduce a partial order. They're not totally ordered. So let's say I verify a program where I unroll the inner loop once on the right side and the outer loop twice. That does not imply verification or correctness of the left-hand side program. And this is simply because the program paths on the right-hand side are not anymore contained within the left-hand side, or the left-hand side is no longer contained in the right-hand side. So there's some elements that are still ordered, but some are not ordered. So let's see how we can actually use this to our advantage to do some search procedure. So the question we have now is, how do we know which local unroll bounds to use for verification? So here's one way we can do this. So imagine you have this lattice we represent with a Haas diagram, and every element here is an assignment of local unrollings for a program with 2 loops each. And we have an upper unroll bound of 3. So let's say we want to verify this for the purposes of the example up to a global unroll bound of 3, which means every loop is unrolled 3 times. So we create this diagram where we enumerate all elements or all possible assignments of local unrollings. And the edges here represent the orderings that exist between the elements. So for example, I can order P1 of 1 and P2 of 1, but I cannot order these 2 elements. So any elements above or under other elements in this lattice can be ordered. So one way to do this incremental verification approach is, let's say I start with the bottom element and I query Alive2. I say unroll everything once, and it says, OK, everything looks correct. Then I keep enumerating up this lattice, and it keeps saying things look correct, but then you get a timeout eventually. So when you get a timeout, because we have this partial ordering, this actually tells us some useful things, such as the elements above it, which contain the traces of the timeout elements, we can trim those, and we can say, these will potentially also lead to a timeout. And then we can continue verification in our lattice. And let's say now we find a bug. And this also implies that bug exists in the elements above this lattice or in the upward closure. So this is one way we can search the space of local unrollings. But this kind of is inefficient. Let's say this whole lattice can be verified. We have to enumerate k to the n times, where k's are unroll bound and n is the number of loops. So what's another approach we can do for this? So this is, in practice, when we ran this, we ran into issues like this. Like it would take forever because the whole lattice could be filled up to a certain limit. So in practice, we actually use a different approach. So key idea is you pick a node randomly, you query Alive2, and let's say it tells you it's verified. Now you can trim nodes in the downward closure. So you have, in this example, we have more elements. We trim those, and we imply the verification of those. And then we pick another node randomly. We get a timeout. We trim nodes in the upward closure. And I pick another node. And let's say I found a bug. So here I can conclude I did not have to explore all elements in the lattice. So it's like an easy way to trim the search space. And yeah, so this example, there was a bug. Some cases you don't have a bug, but this lattice approach is still useful because you can increase your verification coverage. So you can perform this until the whole lattice either becomes green or you have timeouts, right? So we evaluated this approach. So first we extended our live 2 with these local unroll bounds, and then we had this lattice search and prune procedure implemented, that I just showed you, implemented on top of a live 2. And we evaluated this on TSVC, OJENC, and SQLite. So the main benchmark here was TSVC because it contains many loops for each function. So that was the main goal of the benchmarks, like to evaluate this on functions with loops. So we take each function from the benchmark, we compile it with LVM and do an O of 0 and O of 3 optimization. So that gives us the pair of programs. And then we feed these two into a live 2 or into our lattice search procedure. And we set an unroll bound of 15. So in those previous slides, we had that upper bound of 3. We use 15, so the lattice is actually huge. And we set a timeout of 10 seconds for each query to a live 2. And the output of this is a coverage metric statistic. So it's basically that thing I just showed you previously. It's how much elements were covered or verified in your lattice, right? So here's what the results look like. So for TSVC, there was 119 functions we evaluated this on that contained between 2 to 5 loops. And we saw a coverage increase for 56 of, oh no, sorry. I think like 20 something of them. I did not write it here, but it's in this top chart right here. So I'll go over one of the examples, but the orange here represents a coverage increase over the best possible verifiable unroll bound you could have gotten with a live 2's global unroll bound. So I'll show you what that means in the next slide. So also, if you're wondering why there are so few functions from these other two benchmarks, that's because the functions for these benchmarks actually, they contain not just loops, but a lot of other code in some loops. So a live 2 was timing out irregardless of the unroll bounds we use. But for TSVC, most of the functions are strictly just loops. They don't have extra code above or under them. So that's why there's some more functions we're able to verify there. So let's go into TSVC's example for this function. We had these 3 loops, and with local unroll bounds, we were able to verify elements like P of 15, 15, 6. Those are the local unroll bounds we use. But with global unroll bounds, we could only verify global unroll bound of 10. So to get to 15, or these elements, we'd have to verify somehow a global unroll bound of 10, and that was not possible because it timed out at a global unroll bounds of 11. So that's just the example of some nodes we're able to verify. So some limitations of our approach is we only support optimizations that preserve the number of loops. The lattice space can blow up easily. And we also don't use any static analysis on the program structure. We just use this random search heuristic that I showed you. So you can try out our tool. We're currently upstreaming this into a live 2. It preserves backwards compatibility. So you just give the unroll bounds the same way you normally would, and you can use comma-separated lists for the loops in the order they appear. So yeah, that's it. Thank you, and I'll take any questions.
Okay, any questions?
Hi, thanks for the talk. As far as I know, software model checkers, they also use some unrolling loop strategies.
Yes.
Could you compare your work with this work?
Yeah, so I'm aware that model checkers like CBMC, they have you can provide individual loop unroll bounds. We didn't necessarily compare it with them because our comparison wasn't between a live 2 and other model checkers. It was just to see how many more programs can we verify, specifically in the case of a live 2. And a live 2 also works on LVM IR. Yeah, I think it's like CBMC. I'm not sure what representation they use. I believe it's just on C. I'm not sure actually. But yeah, model checkers have had this unroll bounds thing for a while now, so it's not a new idea. But this lattice procedure we implemented on top of this was the main thing we wanted to evaluate. Yeah.
Okay, any other questions?
I got a question. The sequence or the order we pick in random nodes may affect the final performance of the tool, right? I just wondering how it could vary among the different random choices.
Well, is your question between different program loop structures, how the random heuristic
yeah,
varies?
for a single program, maybe different random choices may have different performance. I'm just wondering how that could vary.
Yeah, you're asking about the variation between it. We actually, I do not have measurements for variations between random programs. But what I can tell you is with our we had earlier heuristics for this. So we would look at the number of code blocks in the loops, and use heuristics for exploring specific loops individually. And we found even with all those heuristics we had, or starting from the bottom of the lattice or the top of the lattice, the random approach worked better than the other ones. We would get many timeouts with the other approaches. So that's kind of why we settled on just a random approach, which worked. It's a very simple idea and it worked well.
So it's chosen by experiments?
Yeah.
Okay, by sampling.
Yeah.
Thank you.
Good. Any other questions? Okay, I have a couple of questions for the evaluation. So first, why did you choose this TSVC as the benchmark?
Yeah, so this is like, I guess it's a very popular benchmark for vectorizing compilers, but all the functions contain just strictly loops. So this is working on loops, right? If we have a program without loops, there's really nothing to evaluate here. These other benchmarks, I think, give a good reason why TSVC was useful. These benchmarks, the functions just contain, they're like huge functions that may contain some loops in them. They specifically have between 2 to 5 loops, but they have a lot of other code between the loops. And we actually did not get much of a performance improvement because regardless of the unroll bound we use, it would just time out. So even if we use the unroll bound of 1, the lowest amount, it would time out.
Okay.
So that's why this loop TSVC was actually a pretty useful benchmark.
I see. So did you
yeah.
try any real-world logic program, and what is the largest program you tried?
Yeah, the largest was probably SQLite. So this is like some of these functions are very large. I don't have an exact number, but if you go to the SQLite benchmark, this is just one C file. It's a huge like C file. And I forgot how many lines of code it is, but we did not get much of a performance improvement strictly because a lab2 would time out regardless of your loop unroll size. Yeah.
Okay.
But that's one of the limitations here. Yeah.
Okay.
Yeah.
Let's thank our speaker again.